Greetings and welcome to video V7. Here we're going to look at some population biology issues. You see some of our focus questions here. Defining a population, some of the most important aspects, things that ecologists care about, really, with populations. How do populations change size? And how might the environment actually influence a population? Let me show up here. Ooh, okay, hang on. Let me change here to a little smaller size. Here we go. And let's look at these questions then, one by one. What? Ouch. I'm going to roll all the bees around me. Okay. Let's consider first the definition for a population, just so we're all speaking the same language here. To an ecologist, a population is a group of potentially interbreeding individuals within a given area. And this might seem like sort of an odd definition when you think about it, potentially interbreeding. Here we're talking about members of the same species. So all the members of us in a certain area that might potentially interbreed, that is, they're all of the same type within a given area. That's another kind of a weird phrasing, but this refers to the fact that a given area that the population may interact within. In other words, I wouldn't consider all the squirrels in North Carolina necessarily a population that I could study because all the squirrels would not necessarily interact because they're too far apart. But the size of a small forest might be a really good population study to do on squirrels. So in short, the given area depends kind of on the population itself. Biologically, the mushrooms growing in a yard might be a good population to study, but mushrooms growing in the entire United States would be too big and would be hard to study, and they're not all necessarily going to be interbreeding. So that definition, while it's a little odd, is somewhat flexible given that populations are going to be different based upon their biology. So with that, let's go on to this. What are some of the important aspects of populations that ecologists do study? That is, what do we really want to know about a population if we can get a chance to study it? We want to know, I'm just all over the place here, we want to study how many individuals are in the population, and we'll look at some examples of why we want to know that in a second. Another feature we want to know about a population is density. How many do we have per area? It's one thing to say you have 20 individuals, but 20 individuals in a classroom and 20 individuals in a smart car, a little different study. We also want to know distribution. How are they spread out? Are they in any kind of pattern when we're looking at the individuals of a group, or are they more randomly distributed? And age structure. How many individuals do we have in different age groups or age categories? And we'll look at an example of that in just a moment. So let's start with size and density. We'll just review why these are even important first. The number of individuals in an area is important because it tells you something about how they're going to use resources. And there's a big difference between having 3 ducks in an area and, let me get out of the way, and having hundreds and hundreds. So size is the number of individuals, and it can vary obviously from small to large. But why do ecologists care about this? Here are some examples of when this would really matter. Think about an endangered species. If you only had, let's say, you're down to the last 3 ducks, knowing how many ducks you have is important. Or let's say you have an invasive species and now you're trying to count hundreds and hundreds of individuals. Even knowing that you have a very large population tells you something about its potential impact. The other area that we want to care about is something like hunting limits. If the North Carolina Wildlife Commission wants to decide how many deer that hunters can take this fall, they need to have some estimate or some idea of the number of individuals that are out there, and perhaps we'll do some estimation exercises so you can see how this works. So the number of individuals does matter a lot, as does density. Density is the number of individuals you have in a given area. Now let me just show you this map. This is showing you the density distribution of the United States population in 2010. The darker the color, the more dense. That is, when you're at this very dark color, there's more than 530 people per square mile. When you're looking down here, you're saying 110. I think where we are, it's a little hard to see here, we're about I think we're about 160 people per square mile here in Lee County. But that just shows you that the distribution of our populations, density-wise, is varied. We go from areas like we see in New York or in Florida, parts of Texas or California, where we have very high density, to most of Alaska is very low dense populations. Some of these areas here are going to be in the order of 0 to 50 people per square mile. So they're really spread out and the density is low. Another thing we want to consider then is how they're distributed. If you could look at a population, look at its individuals, how are they spread out in the area they're in? So here we have the three basic patterns. Let's start down here at the bottom as cut off down here, but it's uniform. This is very common for birds and other territorial animals. They are rather evenly spread out, as if somebody kind of planted them in different spots in the forest or in this case on the sand. So the dots here represent individuals, and you see how they are roughly evenly spread out. And this is because all the individuals have their territories. This one's territory is like this one's territory is like that, this one's territory is like this. So this, you see this in, that one's territory is not so good. You see in areas where they have territorial displays in a population that you might have more of an even distribution because of that. So uniform is one kind, and again it got cut off down here, so let me write it here. So uniform, and I shouldn't have written it because it's hard to write with a mouse. Uniform. So that is one distribution type. Another type, one that's more common, is clumped. And this is not the best picture to show this, but if you're looking at plants, for example, growing in a certain area, you may see quite a few plants of one type like this in one spot, and then there's whole areas where you really don't see any plants growing or none of that type, and then you may have a couple more over here, and then you may have some over there. Why do you see this pattern? How often are resources going to be evenly distributed in an area? Not too often. So because of resource differences, resources tend to be randomly, well, not randomly, they tend to be clumped in terms of their distribution. So things growing on them or things using them are also going to be clumped. So again, they use fish for an example, not the best one to use here, but that's just trying to show you the fish are not evenly spread out through the sea. They're going to be more localized and clumped. And the last pattern is random. And random is not as common as you might think because resources aren't random. And the only time you see really random distribution is when you see populations that are often wind distributed, like when you're blowing pollen and you're blowing seeds around, then there really is no particular pattern where you may find a specific population. They could have one individual here and then another individual could be there. And you don't see really any clumping. You see them more just, so they're not distributed uniformly and they're not clumped. So random is the last pattern. Okay. Onward to age structure. Age structure is one that demographers really care about. Demographers are those who study populations from a looking at different features of a population that might be influential in the future. So these age structure diagrams are actually really interesting to study and to look at as kind of predictive models of the future. Let's look at two age structure diagrams here. This is the United States. And what it's showing you here is the percent of individuals of a certain gender in a certain age group. So down here, for example, if I look at this first green bar and look at right about here, it's telling me that this bar here represents about 10%. About 10% of the U.S. population is a male under the age of 4, or between 0 and 4. is showing here that roughly about 10% of the population is a female between 0 and 4. I can come all the way over here to this one. It's showing you, if I were to look down all the way, so I can draw a straight line, it's showing me that, let's say, 11 or 11.5% of the population is a female between 50 and 54. So it allows me to look at a slice of a population and look at, again, what's called its age structure. How many individuals, or what percent of individuals of that population are in that age group. And you can notice a couple of things that are really intriguing about this. One is you notice that the female side is much higher or much longer than the male side, especially in the later years. Why is that? Females typically outlive males. Sorry, guys. So you tend to have a higher percentage of females than males in this highest age group. The good news, guys, if you get to be an 80-year-old male, there's going to be lots of 80-year-old females to date. Good news. You also notice we have kind of this bump, this kind of extra piece here sticking out, an extra piece here sticking out, and a little bit of a piece here sticking out, and one here as well. Do you know what we call this group here of individuals who are in the 40 to roughly 59 group? These are the baby boomers. So we had up when the soldiers came back from war in World War II, they came back and celebrated, if you know what I mean. And when they celebrated, there was a bunch of babies born in those years when the soldiers were returning, and those are called the baby boomers. So that group that it was born between 46 and 64, somewhere in there, since there was a lot of babies born, you had kind of an extra bulge. And as that population got older and older and older, that bulge just persisted. What do you see down here? Why is there this extra bulge down here? This is called the echo, because when the baby boomers started having kids, because there's a lot of baby boomers, there's lots of baby boomer kids, or echoes. So we had a little extra bump down here. So you can see the U.S. population, you can actually do quite a bit of analysis and say, how many schools might we need? How many nursing homes might we need? Because as you can see here, for example, as the baby boomers get a little bit older, they're going to have more and more need for more and more geriatric services. We're going to have more and more need for probably prescription services for seniors, for example, or more doctors to work with that population, because we're going to have a bunch of people aging out. There's also implications for our society, because as they stop working and retire, it's going to take a lot more money for us, those people who are still supporting them, to support them, because there's going to be a bunch of them. Over here, take a quick look at, this is Ethiopia in 2010, and you'll notice some big differences. First, you'll notice how there is not a lot of old people in Ethiopia of either gender. They don't typically have a long lifespan there, and that's because of medical conditions and food and other resource limitations. So we have that issue. We also see this, and this is where it gets a little scary. Notice how it's pyramid shaped. So what does that mean? It means you have a lot of people here that are young relative to old. So as these people get older and they start having babies, then the pyramids is going to get wider and wider as the people who can have kids get older. The reason they have this as blue, by the way, these are the people who could have kids. So you see there's a lot of people here who could have kids, as there are over here. But since the population is so wide, as it ages, it's going to get wider and wider and wider. Said differently, if every person here has 2 kids, and then their 2 kids have 2 kids, and then their 2 kids have 2 kids, it's going to get wider and wider and wider. Our average age is 38. Their average age is 17. When the average age is very young, it means you're going to have a lot more kids in the future. And that's of a big concern for countries that don't have a lot of resources, like Ethiopia. So a good question to ask then is, which country is going to need more high schools in the future? And I think it's pretty obvious from this example. Ethiopia is going to have a lot of needs for the young. We're going to have a lot of needs for the old because of our age structure diagram. Let me just show you one more that gets at some kind of human population growth issues on the planet. Once again, you see Nigeria has that pyramid shape. That means rapid growth. There's going to be a lot of kids having a lot of kids having a lot of kids. Our growth pattern here, again, you still see the bulges, but our growth pattern is a little more shaped like that. And because it's shaped that way, it's a little more column shaped. Let me draw it. Sorry, hard to see the hands. Since it's a little more column shaped overall, then this is a population that's growing more slowly. When the population, when the age structure diagram tends to do this, tends to go in toward the top and it's narrow toward the bottom, this is a population that's actually getting smaller. These people here who could have kids are having very few kids, rather than in the U.S. where the average person, lost my pen, in the U.S. the average person here has about, the average couple rather, has 2.1 kids. In places where the population is declining, it's like 1.6. Over here, it's like 4 point something, 4 point something. So there you tend to have populations that are growing a lot faster. This one is growing much more slowly. This one's actually declining. So you're seeing the population growth in the countries, across the world, they're not even. In places where you have a lot of young people, you're having a lot of growth. Places like Nigeria and Mexico and parts of Asia, in parts of Europe, you're seeing declining growth, and in the U.S. it's very slow. Okay, let's begin to wrap up here. I want to show you this quick explanation about populations changing size. This might seem kind of obvious. How do populations get bigger, Mr. B? There's more people born, or there's more things born, or more things hatched. True. That's referred to as birth, sure. The better term is actually natality. That's an A. Natality refers to adding individuals through reproduction. So, sure, birth and natality, we get it. That's how populations get bigger. They can also get bigger by immigration. If you have a group of individuals here and a group of individuals here, and I'll draw some individuals real quick, okay, and over here you have some as well. If individuals and we'll call population B, if they migrate, if they immigrate this direction, then this population is getting bigger by immigration with an I. Okay. Deaths can just subtract from a population, and the term for deaths here is mortality, and it's really hard to write with this. Mortality is how populations get smaller because there's death. Individuals die. And they can also get smaller by immigration when individuals go the other direction. This population, population A, is getting smaller as individuals immigrate. It's pronounced the same way, but as they leave, populations can get smaller. So populations get bigger through births or natality and immigration. They get smaller by deaths and immigration. So usually we kind of just pretend that the immigration and immigration are kind of equal, and when we do that, we come down to this conclusion that the rate of change, I'm going a little fast now, the rate of change can often be looked at as the difference in births and deaths. So let me get my marker again. So the rate of change is a difference in births and deaths. If I have a lot more births than deaths, the rate is positive, and I'm adding individuals to my population. Here's just an example of how this works. If a population, oops, I have a typo, sorry. If a population of 1,000 individuals has 150 births and 50 deaths per year, what is the growth rate? Well, if I just do the math, and you don't have to do the math very much in here, but if you do the math just to see this, if I say, let me get my marker, if I say 150 individuals out of 1,000, if I do that, that actually equals 0.15. Okay, what it's saying is, that's a point, What it's saying is every individual in the population basically is going to add, through reproduction, 0.15 new people, or 0.15 new things. 50 deaths per year is going to turn out to be 0.05. So if I subtract those, it's 0.1. In other words, I want to be adding, basically times 100, I'm going to add 10% of the population a year. If you do the math, you can sort of see this. I'm going to add 100 individuals to this population every year at this birth and this death rate. So every year, I'm going to have about 150 births, natality, 50 deaths, mortality. The net increase is about 10%. That's a population growing really, really fast. So that is important. But what if R is negative? What if we have a population with R being negative? If R is negative, then the population is declining. So if we have 20 births and we have 100 deaths every year, the population is getting much smaller. And finally, let me erase stuff here. How does the environment affect the ability of a population to grow? How does the environment, the amount of water in this case, or food, affect the population? I think you know the answer to that. Obviously, it's going to have a major effect on population growth, and we'll look at that in class. When we talk about, again, the abiotic factors like temperature and water and nutrients and food and other sources that the populations rely on, then the population is going to be largely dependent upon its resources. So we'll look at that next time. This video is long enough. We're done. Thank you.